All right, so far we've talked about kinematics, which is how to predict the motion of isolated objects. We've talked about dynamics, which is sort of how to predict the motion of connected objects. So now we're sort of moving into a slightly different territory. But I like to think of it as we're still going to learn how to predict the motion of things, but now we're going to learn how to do it in a slightly different way. And in some sense, when we apply the rules of work and energy to predicting motion, in a lot of the cases, it'll be easier than what you've already done. So the idea is to be able to attack similar sorts of problems, but in sort of a new way. And where we're going with this is to be able to eventually apply, to predict motion between interconnected objects and understand what happens when they collide and things like that. So we haven't really looked at, we've looked at independent objects, we've looked at two objects that are connected, but nothing about what happened before they're connected and what happened after they're connected. So that's sort of where we're going. We're slowly branching outwards and taking a larger bird's eye view of the processes that are taking place. All right, so we need to start off by defining energy. So what is energy? Who's got a good definition for energy? Sorry? Capacity to do work. That's like a textbook. Capacity to do work. Of course, the problem with that is, what is work? All right, so that's kind of a textbook definition. And work is not necessarily what you think it is. We'll come back to work in just a second. Another good definition might be, instead of saying work, like the cost of doing something, the cost of executing, of doing an action or something like that. So we start to think of words like how hard is something. So if something is hard to do, we say that requires lots of energy. And conversely, if it's easy, then it requires little energy. All right, I'm going slightly in a different order, a little bit different order than I've done so far, but I want to mention the unit. So the SI unit for energy, just to get it in your head really quick, for energy is the joule. And now joule, of course, is not a fundamental unit, so we can break it up into its fundamental units. If you do so, 1 joule is equal to 1 kilogram meters squared per second squared. And the very astute among you will recognize that a kilogram meter per second squared is equal to a Newton. And then you throw in another meter for good measure, and you get a Newton meter. So 1 joule is often referred to as a Newton meter, or a kilogram meter per second squared, or whatever. So I mentioned the SI unit of joules, so we can take a look at what is a joule. Or how much energy is a joule. So a couple of examples. If you, being an average person with a 2,000 square foot house and 2.5 kids and 3 cars or whatever it is nowadays, average person, if you stand up, that takes about 300 joules of energy. If you drop a ball from 1 meter high, that's 2 joules. All right? In other words, a joule is not really all that big, which is a good thing, because if you go to McDonald's, I went to McDonald's last night for my son's birthday. I'm like, where do you want to go to dinner? Anywhere you want to go. Remember, Daddy's favorite restaurant is University Cafe. Anybody been to University Cafe? One person? Seriously? It's fantastic, isn't it? It's great.
I like Kang's better.
You? I've heard that. I think they're pretty similar. But I've never been in Kang's. I've only eaten Kang's. So, University Cafe. I mean, come on. It's maize and blue. It's like all Michigan all the time.
Where is it?
Cool little. It's on Church Street, on just off Southview, right across from Pizza House.
Oh, maybe we
fantastic. So anyway, I told my son, like, University Cafe, wink, wink, Amos, are they like Amos? No, he's like, McDonald's, Dad. I'm like, so if you go to McDonald's and you eat, McDonald's if you get a Big Mac. So where was this going? It's a good thing a joule is a small amount of energy, because if you eat a Big Mac, you are eating 2 million joules. Right? So that's that's oddly enough, I think if you eat a 12-inch sandwich from Subway that isn't, like just turkey, you get more than that. So, be careful. Choose like I do. If I'm going to go out to lunch, you know where I'm going? I'm going to Taco Bell. All right, so a joule is pretty small. Another way that we talk about energy on a day-to-day basis is we buy energy every day, or at least most of us do. We get our energy, I get my energy from DTE. Who knows the unit of energy that they use? If you look at your bill, kilowatt hours. Danielle, you were shaking your head. You don't look at the bill, you just pay it. Here's my money. Take my money. All right. Actually, my wife does the DTE bill, so I never see how much energy we use. Whenever we spend less than the year before, so like, let's say she goes back and compares like this June with last June, she'll be like, oh, we used 10% less energy this month. But she'll never tell me the months where we used a bunch more. And it's like, it's sort of, how our psyche works as humans. We're always really proud when we do good, but we sort of try to sweep it under the rug when we don't do so well. Right? And then the physicist in me is like, well, you're only comparing 2 months. Let's take, we need to know, 20 years. Let's take a look at the running average for 20 years. 2 months, the weather's different. Can't explain. It's not that we're doing better. The weather could have been different. Anyway, so if you look at a bill, I looked online the other day, and it was 6.912 cents per kilowatt hour. That's how much you're charged, and that's actually like for the first X amount of kilowatt hours. Then it changes after that. I'm pretty sure that DTE charges you it's not very clear how they charge you, so that you don't argue with them how much they charge you. So anyway, I found a number 6.912 cents per kilowatt hour, which is that's not really what they charge. It's more than that, but let's just go with that number. So I want to know how much am I being charged per joule. We'll get to this in a little bit, but 1 kilowatt hour, that's actually a unit of energy. So a kilowatt hour is actually, you can convert to joules. So that's 3.6 times 10 to the 6 joules. It's 3.6 megajoules. I'll show you this probably later today. Just take my word for it now. So if you do that math, you get 2 times 10 to the minus 6 cents. That's how much it costs per joule. So cents per joule. All right, so just a tiny little bit, but a joule is not a very large amount of energy, so it adds up. All right, so let's take a look here. We're going to deal with several different types of energy. And this is the reason that I started with the unit, because we're going to deal with a bunch of different types of energy. We are going to do with energy in the form of work. So Shane already mentioned work. Your book does not state this right up front. It makes a separation between work and in Chapter 7, kinetic energy. But I would just want to tell you right now, work, energy, it's the same thing. All right, so your book does it in a nice way. It presents the material in a great way so that you guys can sort of step through and learn things. But I just want to be clear from the beginning. When I say work, it's energy. It's just a type of energy. We're going to talk about kinetic energy. Does anybody know what kinetic energy is? Energy of motion. If you're a kinesiology major, you say kinesiology, kinetic, motion. Okay, makes sense. We're going to talk about potential energy. Does anybody know what potential energy is? Sort of, it's related to position. Potential energy you can think of as the ability of something to do work, how much energy is stored within a system. So potential energy is usually like stored energy that's stored internally somehow. So in this class we'll talk about gravitational. We're also going to talk about elastic or spring potential energy. There's also electric potential energy, which we won't deal with in this course, but you will if you go to Physics 222. And one other form of energy we're going to deal with is heat. So heat is energy. It's just another form of energy. All right, so let's start in on that list, and let's commence by talking about, what is that? What happened? I did something magical. Let's start by talking about work. Work is a form of energy, and in fact, it's the energy required to exert a force. All right, so work in our day-to-day life is our job. Work in physics land is the energy required to exert a force. So the most fundamental way to define work in equation form is work is just a force times a distance. All right? So if you apply a force over some distance, you are doing work. All right, now note that this sort of doesn't agree with another one of our conventional maybe thoughts about what work might be. And that is if you do work, if you exert a force, but you don't move anywhere, then you're not doing any work. All right, which is, a bit intuitive. I sit at a computer all day. I sort of exert a force on the chair, but I'm not really doing any work, which you could probably make a good case for. So another way to write this down, though, in a more general sense, that this distance is not just a distance. It's actually the distance that is parallel to the direction of motion. Okay, so I've already started to quantify this equation here, which is why I didn't write it down in terms of letters, because that's how we write everything down in physics, is in terms of letters. So I'm quantifying this sort of equation, and so now I'm going to write it in a new form that sort of takes into account this parallel sort of thing. All right, so I'm going to write down an equation for work. W is equal to F vector force with a big old dot D vector. All right, so this is the proper definition of work. And that big old dot thing isn't just the normal multiplication thing. That is called the dot product. All right. So the dot product is something unique to vectors. It's a vector form of multiplication. All right, vector multiplication that results in a scalar. Whoop. Okay, so note it results in a scalar, so work is a scalar. Energy is a scalar. Energy does not have a direction associated with it. Okay, so how does the dot product work? Well, in general, if I have two vectors A and B, and let's say those two vectors point in two different directions, two arbitrary directions, and they're separated by some angle theta, then I can calculate the dot product of the vectors A and B by taking the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. All right, so that's the dot product. Who's heard of the dot product prior to this class? All right, just a few of you. So it's just a new way to multiply vectors. Don't make it more complicated than it is. It's just some special vector multiplication. It is dependent on the magnitudes of the vectors, but it's also dependent on their direction. Okay, so we got to treat things a little bit differently. All right, so this cosine of theta thing, that adds in a little bit of complexity, but you'll see why we do that in just a second. Okay, so let me illustrate that via sort of a simple example of calculating work. So imagine that I'm just pushing on a block. So I'm exerting a force on this block, and that block is going to move. It's going to move 5 meters, so that eventually it ends up down here. All right? So I can calculate the work done by this force F. So this is some force. I want to know, what is the work done by F? What is the work done by the force F? Okay? Well, my definition of work says that the work done is equal to F dot D, or that dot is the dot product again. So that's got to be equal to the magnitude of the force F times the magnitude of D, which is the displacement vector, times the cosine of theta, the angle between the two vectors. So in my problem, the force, I'm just going to draw the forces off here to the right. The force F is in this direction. The displacement D is in this direction as well. So theta is 0. They're pointing in the same direction. All right, if theta is 0, then, yeah?
Is there a reason why the arrow for direction is bigger than the arrow?
Just because I want them to look different. Yeah, I'm sorry. I'm just trying to make them not look identical. Arbitrary. All right, so the angle is theta is 0, so cosine of 0 then is just 1. So what you get is work is equal to force times distance, basically. All right, which was our original definition. If you look in your book, it sort of starts with this definition. But I just want to point out that this isn't correct. This is the definition of work, the dot product. You got to take into account the angle. But if the direction of the force is the same as the displacement, then it's simplified. Okay? It does show the dot product in your book, but it starts the other way. So if I give you the magnitude of the force, let's say that the force is 10 newtons, then I can solve this. That's equal to 10 newtons times 5 meters, or 50 joules. The amount of work it takes me, the amount of energy it takes to move this mass 5 meters is 50 joules. All right? Pretty straightforward. All right, so let's do this example. Let's put the block on an incline. All right, so now I apply a force. I still apply my force horizontally. It's still 10 newtons. But this time, I did a bad job of drawing I'm still in the habit of drawing force problems. All right, so this time our block is going to move up the ramp. Still a distance of 5 meters. All right, and we're pushing it at 30 degrees. Okay, so this time force is in this direction, but the displacement is up here. And this is 30 degrees. Okay, now imagine what's going on here. Cheeks, you have a question? Why is the force horizontal? Well, why not? You mean this? Why is it horizontal? How would you rather the force be? Up the slope? Am I not allowed to apply a force horizontally? So, okay, fine. You're saying if the force is horizontal, why does this move up the slope? Is that what you're asking? So, would you agree with this statement? If I apply a force horizontal, there's a component of that force that lies along the direction of the slope. Yes? Really? I mean, the way that you're saying, okay, I believe you, which is good because, I mean, that's not incredibly obvious, right? Maybe 2 weeks ago you'd have been like, what are you talking about? But yeah, I mean, so I would argue that there's definitely no way that if I apply a force in this horizontal direction, then that block is going to move up. That's not going to happen. But I could certainly apply a force in this direction and have the block move on an incline. You know, imagine that you're pushing a shopping cart up a ramp. And you could push the shopping cart straight and it's going to go up the ramp. It would make more sense if you wanted to be efficient about it to push it up the ramp. Sure. And that's what this example is going to illustrate. All right, so here so it's not as simple as the other example. All right, so I've got a force that's not at the same direction as my displacement, so I want to calculate what the work is. Well, we know the definition for work now. It's work is equal to force dot d, which means that I need to take the magnitude of the force times the magnitude of the displacement times cosine of the angle between the two vectors. That's fine. I know my force is 10 newtons. I know that the displacement is 5 meters, but now cosine doesn't go away this time. It's cosine of 30 degrees. All right, cosine of 30 degrees is certainly less than 1. So I expect that this answer to be less than my answer up here. All right, so it took me 40, if you do the math, it's 43.3 Newton meters, I think. All right, so that's how much energy I put into the system. Now, energy isn't free here, okay? So what is the point? I put less energy in, but I didn't travel as far. Or did I travel as far? So I went 5 meters up the slope, but I didn't go 5 meters horizontally. Right? This distance is certainly not 5 meters. So I didn't push the block as far, in quotes, in the same direction. All right? So some of my motion went to moving upwards. Same unit. Yeah, sorry. I like to confuse you by mixing up units, but yeah, it's the same. Joule is a Newton meter. All right? So I gave it less energy, but I didn't go as far in the horizontal direction. So that's the difference there. All right, but just once again, the angle matters. Right? But other than that, the concept of work is not too difficult. It's a force times a distance. Okay? So let me ask you this then. Another really quick example. Here I am on a skateboard, like so. I start at this position here, and I move in this position, in this direction, so I have some velocity. And that distance is 5 meters. The only force acting on me in this problem is gravity, because I'm moving at a constant velocity. So the question is, what is the work done by gravity? All right, who can tell me what is the work done by gravity? I'm sorry? So you're telling me the acceleration due to gravity. I don't care about that. I want to know the work done by gravity. Work done by gravity is 0. Why is it 0? It's not going down. Okay, fine. That's actually right. So while not said in proper physics language, but no, that's pretty close. So yeah, the displacement vector is to the right, the force vector is to the down, force vector is in the down direction, so the angle here is 90 degrees. All right, if I do the actual calculation, the magnitude of the force times the magnitude of the displacement times the cosine of 90 is 0. So the work done is 0. Yeah?
What if we were just to put W equals 0 and then explain that after the calculation?
And explain?
Yeah.
Oh, that's fine. Oh, you're asking for exam again. You guys are always so concerned about the exams. Don't worry about the exam. Worry about understanding. Yeah, that's fine. I mean, yeah, sure. You could even just put work equals 0, and I'd be fine with that. Okay, so yeah, work is 0 here. Even though there is a force acting on this person, it's perpendicular to the direction of motion, so the work is 0. I want to point out something, and this is something that trip people up sometimes, okay? When you're doing homework on the next homework assignment, when you start to come across work, you'll see problems where where the WebAssign asks about the work done by a specific force, or you might see problems where the WebAssign asks by the work done by all forces. Just be careful about that. So we could calculate the work done by a specific force. Calculating the work done by all forces means you have to calculate the work done by each individual force and add it all together, or something like that. Right? But you'll see both types of questions. You'll see another one in a little bit here as we go forward. All right? Okay, next question. Come on, come on, come on. Go. Got it. All right. Another example. You're standing in an elevator. The elevator takes you from the initial position up a couple floors. Who cares? 10 meters. We'll say it's 10 meters. All right? And I ask you this question. What is the work done by gravity? I'm going to give you the gravitational force. It's equal to 700 newtons.
Is that the downward arrow?
Yep. I'm going to label it just 1 second after I move this down so it's not all squished together, all ugly like. So right, this is the force due to gravity. So what is the work done by gravity? All right, so the work done by gravity is the magnitude of the force times the magnitude of the displacement times cosine of theta, which is just 700 newtons times 10 meters times cosine of 180 degrees, which is -1. So the answer is right, -7,000 joules. Does this seem weird? How can the work done be negative? What does that mean? You're not going down. Gravity is pointing down.
Because the work done by gravity is pushing you in the opposite direction of where you're going.
All right, so gravity is trying to push me in the opposite direction, but I'm going up. So that means that the work done is negative. Now, what the consequence of that is, and you'll see this as we go forth and talk about changes in energy and things like that, is what this means is that gravity is giving energy to the system. So as I move upwards, basically I'm taking energy from gravity and storing it in my system. Okay? You'll see this more as we go forth and talk about potential energy and conservation of energy. But anytime you see a negative number, what that means is the system, in this case, the person, gains energy. So let me write that down. So negative work the system or the object gains energy. In this case, gravity is doing the negative work. If you have positive work, the system spends energy. Okay? Simple sentences, but really difficult concepts to really understand. Even in this context, we have a single force. You say when we move up, gravity is giving the system energy. Later on, if I want, I could get that energy back by moving down, by falling. Okay? But we're going to get into scenarios when there's multiple forces acting. And so, yeah, the system may be moving one way, so it must be gaining energy, but all the other forces may be giving or taking away energy. So you can imagine having gravity and a spring doing something, and maybe, I don't know, an electric force pushing on the person. I don't know. But when we have lots of different forces, each individual force can be giving or taking away energy, but the entire system can only be gaining or spending energy. So you have to sort of add up all the effects of each individual forces to get the net outcome.